Hello, everyone. Okay, I'm Nariaki Tateiwa, and I'm from NTT, which is the Japanese telecommunications company. I'm a researcher at that company, and I'm studying about optimizing the distributed machine learning network backend. So today, I would like to talk about accelerating PyTorch FSDP by using several network technologies. Okay, so here is a brief overview of FSDP. So FSDP is the memory-efficient parallel training method, and it partitions model parameters and optimization states across multiple GPUs. In FSDP, only required parameters are gathered using all-gather collective communication before computing, and release unnecessary parameters after that. In addition, in backward, after computing, the FSDP distributes gradients using ReduceScatter collective communication after computing, and similarly release unnecessary gradients after that. And these two collectives dominate the FSDP's workload communication, so it is important to reduce these communications execution time for the speed up FSDP workload. So this slide shows the existing backward schedule in FSDP. So before training, in many cases, we split model into some SFTP modules. For example, when we train transformer-based model, we split it into some modules based on the transformer blocks. And in each module, we execute altogether to correct parameters, and then execute computation, and finally, we execute ReduceScatter to distribute computed gradient. And this altogether and computation and ReduceScatter process can be pipelined across multiple modules. For example, the module 2's altogether is executed before module 3's ReduceScatter to overlap the computation and altogether communication. So our target in this talk is reducing this entire backward time. So the key idea for that is the Khalilov paper, which was accepted in the FC24. This paper proposes the idea that by combining overlap communication and network computing and multicast, we can reduce the entire backward time of the FSDP. So, okay, but to the best of our knowledge, there was not any studies that evaluate this technique with PyTorch FSDP and zero, so we try to do it. And I note that only overlap the communication is not enough to shorten the reduce the communication time of overlapped ReduceScatter and altogether. So we have to need to use in-network computing and multicast together with overlap. So let me explain why is in-network computing and multicast necessary to shorten the execution time or the communication. So collective communication time is mainly dependent on the longer of sent or received time of each endpoint associated with GPU. And for example, in link algorithm, this is a default algorithm in many collective communication. Each endpoint sends and receives the same data volume during both ReduceScatter and altogether. So therefore, if we overlap them, it does not reduce the total communication time because the total the send data volume and receiving data volume is not changed. But by using in-network computing, we can reduce the receiving data volume of ReduceScatter. So in-network computing is a network technology that offloads some computation operation into the network devices, such as a network switch or smart NIC, and so on. And summation in network switch is a typical example of in network computing, and it can reduce scattered receiving volume to 1 by n-1, and where n is the number of GPUs. And this figure becomes to the half where the number of GPU is large enough. And similarly, multicast on network device can also reduce the all-gathered send data volume to 1 by n-1. And finally, we overlap these reduce scatter and all-gather. We can reduce the total send. We can reduce the both total send data volume and receiving data volume. So we can reduce the reduce scatter and all-gathered execution time by this overlap. So yeah, so by using overlap and in-network computing and multicast, we can reduce reduce scatter and all-gather execution time up to half, where the number of GPU is large enough. So this is a big reduction. So it is very efficient when we apply it to the FSDP workload. So to realize this technique in the PyTorch FSDP, we use this communication bucket setting as prototype. So we use two different communication libraries for each collectives. So we use NVIDIA Sharp for reduce scatter, and we use zero copy spin for all-gather. So NVIDIA Sharp provides summation in network switch function, and zero copy spin provides InfiniBand UD multicast all-gather function. And this zero copy spin is our zero copy expansion of the existing spin library to speed up. And we use UCC communication library as interface of Sharp and Spine library, because UCC can provide power collective routing and easy access to Sharp and Spin. But when we use UCC backend, when we use UCC as a backend of PyTorch distribution directory, it doesn't work, because the UCC backend queues collectives into the single CUDA stream, which is in a UCC backend, and not overlapped the collective communication. So to avoid this construct, we use MPI as a backend of PyTorch distribution, then the core UCC from MPI. And we add some synchronization between MPI collectives and CUDA streams. So of course, this is ad hoc changing ad hoc design for experiment. And I think there is a more simple way to realize the overlap communication into the FSDP training. By the way, with this setting, we can overlap reduce scatter and all-gather in the FSDP training without user code modification. So this is the experiment result using 10 NVIDIA GPUs. And we use GPU, the board series, board 100 GPU. The left side of this slide shows the micro benchmark results of reduce scatter and all-gather. In this experiment, our overlap communication implement was 22.5% faster than naive and nickel sequential execution. And nickel is the default communication backend used in the FSDP. And the right side of this slide shows when we applied the overlap communication technique to the FSDP workload. So of the 3.7 billion models, so we achieved to improve 10.7% faster by using overlap communications. So, and even with other settings, we observed a consistent improvement in backward time of FSDP training. So our approach accelerates both micro benchmarks and real training workloads. So this is the last slide of the takeaways. So by applying communication overlap in network computing and multicast to FSDP, we achieved up to 10% faster backward execution of FSDP workload without user code modification. So this technique is crucial to accelerate FSDP. So that's all from me. So thank you for your listening. Yeah.
What performance speeds are you looking at when you are offloading? Are you going above 100 gig? And then for the scatter gather, how are you able to configure what kind of scatter gather are trying to use? Matmal or summation or something else? Is that configurable? So first was, what is the performance on the network bandwidth you're looking on the SmartNIC when you offload it?
Offload?
Yeah, what bandwidth you're able to see? What's the high end of the, what is the capacity of the offload network SmartNIC chip?
Oh, offload chip, so you say the computation float to the network switch. Yeah, we use the IP quantum network switch, and we use the NVIDIA Nickel Sharp plugin, and we use the ConnectX as a NIC. And so this is the answer.
So are you like, the reason I'm asking is like the DPDK or anything you're using for offload, right? That will kind of start.
I know.
At some performance numbers, right?
Yeah. Only the network switches offload we used. Thank you. Yeah.
Does this technique work with FSDP version 2 and 1, or just 1?
Sorry, please. Again, please.
Does this technique work with FSDP version 1 and 2?
So we explain in our explain we use the FSDP version 1. This result is gained version 1, and so we apply this technique to the version 2. It's now ongoing. So this result is from the version 1.
I have a similar question. Does this work for other parallelism techniques like data parallel or model parallel?
Yeah, that's exactly, yes. So yeah, this technique is orthogonal of the other parallel strategies, for example, the pipeline and the data parallel and so on. So yeah, this technology, but this technology is only can fast the FSDP's backward communication flow. So if the other strategy can combine the FSDP, this technology can use this workload. Thank you.